we have to have a one-to-one function to have an inverse function. Okay, it's a requirement. So now we're going to talk about inverse functions. It says if f is a one-to-one function, notice that's the first thing it says. To have an inverse, it has to be a one-to-one function. And if we have an ordered pair, AB or XY, this notation, this means F inverse of X. This does not mean 1 over F of X. That's what this says. So this is specific notation to F inverse. If I wanted 1 over X, I would have to say F of X in parentheses to the -1 power. That means that this function has a negative exponent. This means inverse, okay? So F inverse of X is a one-to-one function with ordered pairs BA. So what is that saying? It's saying that if I have a one-to-one function and I have some XY, we're going to call them AB, my inverse is BA. I just change it. My range and my domain flip. Okay, that's all that means. Does that make sense?
Yeah.
So the range of the function will be the domain of the inverse, and the domain of the function will be the range of the inverse. They're all saying the same thing, that the domain and range switch for inverse functions with regular functions. Okay.
Mm-hmm.
Okay, so if I start with something like this and I say find the inverse of this one-to-one function, what would F inverse be?
13 -4.
Exactly. We're just changing the domain and range.
7
Okay.
-1.
Exactly. I'll do one more and then I'll just put ... because I think what we're doing is just changing the X and Y as the domain and range. So that's one way to show an inverse function, that whatever values I have, they just flip. Okay. Now, if I start with a function here, I just started with points, right? And I just changed the X and Y values. So here's basically what you're going to do. These are the steps we're going to use when we want to find an inverse function. So if it has an F of X, we're just going to use Y. It's just easier for the algebra. There's no other reason for it. Then we're going to interchange X and Y, and I'll show you again. And then we're going to solve for Y. And whatever value is after we solve for Y, we change the Y to F inverse of X because that gives us our inverse. Okay. So a lot of them are very simple. There's some that are a little more difficult. I'll show you both. Okay. So like, for example, let's do A. So A, first step is I change F of X to Y. Okay, and I'm just doing that literally just to help with the algebra. Okay. Okay, step B, I'll just write exchange X and Y. And what I mean by that is that every Y becomes X and every X becomes Y. So this will be the cube root of Y plus 5. Okay. Then this is obviously the hardest one. We want to solve for Y. So if I want to solve for Y, what would I do here? Any ideas what I could do first here?
Can't you, what is it called? Cube.
Good.
Yeah.
I'm gonna cube both sides, right? So X cubed. So if I do that, here, let me do it in another color. So if I cube both sides, this cancels, and I get X cubed equals Y plus 5, right? And then I want to solve for Y, so I'm just going to subtract 5 from both sides, right? So I have Y equals X cubed minus 5. I just switch the sides. And then the last step is just change y to f inverse of x. Because I've switched the x and y, I now have found my inverse function. So now I know that the inverse of the cube root of x plus 5 is x cubed minus 5. Okay?
Yeah.
Okay, perfect. I'm just going to throw another slide in here, just so I don't have to erase all this stuff. Okay. Yeah, I'll just copy this whole thing that way. I don't have to remember it all. Okay, so now we're going to do B. Okay. So for B, well, I don't want to write it like that. Sorry. So we are going to do B. So we're going to do g of x equals 2x over x plus 1. All right, so what's my first step?
You change the x to y and the y to x.
First, I change g of x. I don't have a y. I change the g of x to a y.
Mm-hmm.
And then I do what you said, which is exchange x and y. So I have x equals 2y over y plus 1, right?
Mm-hmm.
So let's see. This is step 1. This is step 2. All right, now I have to solve for y.
You multiply by y plus 1, I think.
Multiply both sides by y plus 1. So here I'll put step 3. So I have x times y plus 1 equals 2y. Okay.
And then I guess you could divide by 2.
Well,
Well,
but
it's
then I have y in terms of y, don't I? I haven't really solved for y. When I solve for y, I have y equals, and then on the other side, all I'll have is x's and some numbers. I can't have y equals y plus 1 or something like that, right?
Mm-hmm.
And if I divide both sides by 2, I'll have y equals x times y plus 1 over 2. So that's not going to work. And you really, if you divide by 2, you're going to end up having to deal with a bunch of fractions. And I don't recommend that. That's why we divide last whenever we solve for things, because it just makes fractions. So this is the harder one. So if you don't know what to do, I understand this is not the easy one. This is the harder one. Well, just probably because I haven't shown you how to do it yet. So
you don't distribute, do you?
You do.
You do.
Distribute.
Okay.
So the next thing we're going to do is we're going to distribute that x. Because think about what we're trying to do. Whenever we solve for a value, we have to get all of those values on one side, everything else on the other, right?
Mm-hmm.
So are all my y's on one side?
No.
So that would be where I would want to start. I want to at least get all my y's on one side, because that way I can maybe manipulate it a little bit, right?
So you can divide by y again?
Well, I don't want to use division. Every time I use division, first of all, let me say this. I'm going to probably say this a few times, maybe not today, but during the class. You rarely want to divide by a variable, because unless you know that variable is not going to be 0 ever, if you divide by that variable, if I divide by y and y turns out to be 0, I've just divided by 0 and nothing I do after that will be true. So we really don't want to divide by variables. Okay.
Okay.
So what else, any other ideas? How else can I get all the y's on one side?
I don't really know how to separate those two other than division, so.
I can subtract. Why can't I subtract x, y from both sides?
Well, I thought the whole point was to get.
Well, first I told you, let's get all the y's on one side. So now I have x equals 2y minus xy, right?
Mm-hmm.
Okay, so now I have all my y's on one side, but of course, again, I don't have all my x's on the other side. But Is there anything that you can think of here that I might be able to do to fix this?
I mean,
It's
I would
okay.
say divide, but yeah,
Yeah, we're not dividing. Like dividing is the last thing you
yeah,
always
I
want
know.
to do.
I
Yeah.
then I don't know.
So why don't I factor? I
Yeah,
can factor out a y, can't I?
uh-huh.
And now I have 1y, x equals y times 2 minus x, right? And now I have 1y. If I divide both sides, now I'm dividing because it's my last step. If I divide both sides by 2 minus x, I get y equal, here, I'll do it the opposite way. I get y equals x over 2 minus x, right?
Mhm.
And then the last step just says change that y into the inverse function. So there's my inverse.
Okay.
Okay.
Mhm.
Notice it's not the reciprocal. I mean, I'm saying this because I graded many papers where people say G inverse of X is X plus 1 over 2X. They just flip the fraction. So it is not the reciprocal. You can't flip it. You have to go through the steps and solve it like this. All right. All make sense?
Yep.
All right, perfect. Okay, so now let's look at a function. We're given this function f of x equals x minus 4 squared. So let me just draw it. So x minus 4 squared, hopefully we know at this point that we have a parabola that's moving to the right by 4, right? Do you agree?
Yep.
Okay, so 1, 2, 3, 4. I have a parabola that's moving to the right by 4. And it says restrict the domain to create a one-to-one function. Okay, let's stop there. We can see that we don't have a one-to-one function, right?
Mhm.
Why is it not one-to-one?
Horizontal line test.
Good, because it doesn't pass the horizontal line test. So what I can do is I can do what we call restricting the domain, okay?
Mhm.
So I can say, okay, that's fine. But what I want to do is I want to say f of x equals x minus 4 squared such that x is greater than or equal to 4. Now I have a one-to-one function, don't I?
Yeah.
And what I did is I said, we can only use the part we can also only use the part that's less than or equal to 4. As long as we make it one-to-one, it's okay. I'm going to use the right-hand side. You could use the left-hand side, okay?
Mhm.
So now I've restricted the domain, and now I have a one-to-one function. Restrict the domain to create a one-to-one function. I did that. Now I'm going to find the inverse. And again, we're going to go in steps. So y equals x minus 4 squared. Then we're going to change x and y. What's my next step?
I guess you would square root.
Good. So here, let's say 1, 2. So we're going to take the square root. So 3 is solving. So we're going to take the square root of x is equal to y minus 4, right?
Mm-hmm.
And so I can say y is equal to the square root of x plus 4.
Mm-hmm.
And my last step, I turn my inverse function equals the square root of x plus 4. Okay?
Mm-hmm.
Now I'm going to graph that on the same graph. So the square root looks, well, it looks like this. Okay. And then I'm going to add 4. So it's going to shift it up 4, right?
Mm-hmm.
So it's going to look like that. Okay.
Mm-hmm.
And then it says state the domain and range of both resulting functions. Okay, so here, let's do this. So for the domain, So we'll do f of x first. So for the domain of f of x, well, we already said we had to restrict it, right?
Mhm.
So in interval notation, I can say this is from 4 to infinity, okay? And what's the domain of that function? I mean,
Well-
sorry, what's the range of that function?
Wait, I have a question. So
Sure.
why wouldn't you, I know it says restrict the domain, but it says of both resulting functions. How do you know if it's asking for the domain and range of the restricted function or
It
the
has
full?
to be restricted because otherwise I can't have an inverse. So, here, so inverse functions, notice how it starts off here.
Mhm.
If f is a one-to-one function, then I have inverses. If f is not a one-to-one function, I can't have inverses.
Okay.
It's impossible. So to begin with, because we're finding the inverse, we're restricting the domain and we're saying, okay, we're going to go from 4 to infinity only on this function.
Okay.
Okay, does that make sense?
Yep.
Okay, good. What would be the range of that function?
0 to infinity.
Perfect, 0 to infinity. Okay, now let's look at the inverse function. Okay, what's the domain of the inverse function?
0 to infinity.
Good, and what's my range?
4 to infinity.
Right. And can you know, you should be able to notice here that they're switched. The domain of one is the range of the other. Okay.
Mhm.
And also, I think I'm going to talk about this in a minute, but I'll talk about it now. So the other thing that happens is they are symmetric around this y equal x line. Okay, so I'm going to call this y equal x. Okay, that line. And if I drew it well, which I'm sorry, I didn't draw it great, but can you kind of see that
Mhm.
they're symmetric around that line?
Yeah, it's almost like if you just turned it, it would be like a flip over the x-axis.
Exactly, exactly. So inverse functions are always reflected over the y equal x line. And it has a lot to do with the fact that it's because we're changing the domain and range. Like here, this point right here is 4, 0. Notice the beginning of this point here is 0, 4. And so and it'll just happen like that. Okay. So so they are symmetric. I think that's what this is probably going to say. So verifying inverse functions. If f is a one-to-one function and the inverse exists, then when we take the composition of the two of them, they always equal x. Okay, so if we look at it like this, we can almost look at it like, oh, if I cancel that, I get whatever's left, right? If I cancel that, I get whatever's left. So if I were to draw a picture of this, because sometimes pictures really help. So let's say I start here and let's call this x. And I'm going to go through some function, call this f. And out on the other side here, we're going to get f of x, right?
Mhm.
Now, let's say I call f, let's say I call it x squared, okay? So I'm going to here start with 2. I go through my x squared, and what comes out here is 4, right?
Mhm.
So now I need to, my inverse function is basically going in reverse. So now I'm going to take this 4 and I'm going to go through my inverse function. And my inverse of x squared is the square root of x. Okay. And notice how it gets me back to exactly where I started. The square root of 4 is 2. Okay.
Mhm.
So that's basically what these things are saying up here. They're saying because so for let me do it like this. So for this one right here, this is really f inverse of x, right?
Mhm.
Oh, sorry. So if I start with x, and now I'm gonna have to start with my domain. And let me do this one first because it's gonna confuse you if I do the other first. Let me do this one first. Okay, so I'm gonna start here and I'm gonna say this is f inverse of f of x. Okay, this is where I'm starting. So I am now, so I'm now here, I'm picking my x value, I'm starting on the inside, right? I go through my function, I come out here to f of x, and that's my value, whatever the value is, I'm over here in this circle, right?
Mhm.
And now when I do my inverse, what I'm doing is I'm going back through this function because now this is really this f of x is really my new domain for the inverse function, right?
Mhm.
So notice how it goes back to x. If I go the opposite way, this is actually now where I start. I'm starting here for this function because that's what my input, right?
Mhm.
And I'm going through the inverse and I'm getting to my x value. And then I'm putting that value through my function and I'm going back to where I began. So that's why it's this big circle. And where you start, and if you go through both of those functions, you end up in the same place. Does that make sense?
Kind. So okay. So I'll say for the first function, the one where it says verifying inverse functions, that first one, basically you're doing the inverse function, so like inverse of f of x, and then you take that and you put it back into f of x.
Yes,
Okay.
because this is a composition. Remember when we went through
Yeah.
compositions, this is what we did with, like, if x is 2, like, let's say I start here, we
Mhm.
said here that f of x is equal to, we said here that f of x equals x squared, and we said the inverse function equals the square root of x, because those are inverses of each other, right?
Yeah. Okay. So you're just plugging it in basically.
Right. So if I say here x equals 2, so I'm plugging 2 in for x, I get 4 for f of x, right?
Mhm.
Then I plug in 4 here, and this becomes 4 then, but the inverse is a square root, so I put 4 here and I get 2. So notice I started with 2 and ended with 2.
Yeah. Okay. That makes
And the
sense.
same in the opposite direction. Okay. Okay, good. Now, here's why we need it to be 1-to-1. What if I start here instead of with +2, I start with -2? Well, I start with -2, I square it, I get 4, I take the square root and I go back to 2. Well, I started with -2 and I ended with +2. That's why we have to have 1-to-1 functions, because the inverse has to take me back to where I began.
Mhm.
It's like Little Red Riding Hood going to, if I'm dropping like little things so I don't get lost, I'm dropping little pieces of bread so I don't get lost along the way. And when I come back, I want to follow those breadcrumbs right back to where I began. If
Mhm.
someone else was dropping breadcrumbs, I wouldn't know which way to go, right?
Yeah.
That's kind of what this is. We want to make sure it's 1-to-1 so we know where we start. We can't start with any two different values. Wherever we start, if I go through the function and the inverse, I come back to where I began. That's basically what inverse functions do. Okay?
Mhm.
Make sense?
Yeah.
All right, good. So if the graph of a function passes the horizontal line test, the function is 1-to-1. We already know that. If a function f is 1-to-1, then the inverse exists. So notice if f is 1-to-1, then the function exists. Otherwise, it doesn't. And then again, these two right here are just flipping the domain and range. Actually three, I'm sorry. Domain of F is the range of the inverse, and the range of F is the domain of the inverse. They just flip. This is what we just went over about if you compose a function with its inverse, you always get the beginning x both ways, okay? And what I told you in the last thing, and I showed you, the graphs of F and F inverse are symmetric with respect to the line y equal x, which is what I was trying to point out here. There's a line y equal x, and those two lines are symmetric around that line. Okay, so these are the main properties of inverse functions. Okay.
Mhm.
All right, so let's do this. Use the algebraic method to find the inverse function for f of x equals the square root of x plus 2. Then verify the inverse you found is correct. And then it says we'll graph them. So we'll graph them second. Whenever you, and you have to do this, this is a problem in ALEKS. Whenever you want to verify algebraically that two functions are inverses of each other, you have to use the rule, this rule, that if we compose them together, we get x, and we have to make sure it works in both directions. Okay, if it only works in one direction, they're not inverses. Okay.
Mhm.
So first thing I have to do is find the inverse, and I'll just do that over here. I think we kind of have that down pretty well. So we change f of x to y. We exchange x and y. And then we solve for y. So I have y equals x squared minus 2, or my inverse function is equal to x squared minus 2. Okay, so now I'm saying this is my inverse. Okay, so algebraically I found it. Then verify. Now comes the verification part. Okay, so I know f of x is equal to this, and I know f inverse of x is equal to this. And here's how we're going to do it. So I'm going to say this is the same as f composed with f inverse of x, which is f of, and here's my inverse. So I can say f of x squared minus 2, right?
Mhm.
And now I have to put x squared minus 2 into my function. So f of x squared minus 2 is equal to the square root, and x squared minus 2 has to go where x was, plus 2. And then I can say this is equal to, the line here, this is equal to the square root. Well, x squared minus 2 plus 2, these cancel. Square root of x squared, which equals x, check. Because remember, I wanted to show that that way equals x. Since it does, I showed it, I'm halfway there. I'm not all the way there. I have to do it. I have to do both. One way doesn't make it true. So now let's do it the other way. So I have f inverse of f of x. Well, f of x is equal to the square root of x plus 2. So if I have the inverse of the square root of x plus 2, that equals, I'm now plugging it in here. So it is equal to the square root of x plus 2 squared minus 2. This equals the square root of x plus 2. Sorry. This equals x plus 2, because the square root and the square are going to cancel, right? Minus 2, which equals x, check. So now I know I found the inverse, and I proved it using this method, which this is how you show things are one-to-one. I mean, that's how you show things are inverses of each other. Okay.
Mhm.
Notice it's always x. So I want to point this out really clearly. I've had people have negative x, they both come out to negative x, and they say that's an inverse. That would not be an inverse because they have to be equal to x. They can't both be equal to 1. That doesn't show it's an inverse. It only shows that they're both equal to 1. Unless they're both equal to x, it's not an inverse, okay? So I really want to make that clear. And then let me graph this. I'm going to get a new page. New slide. Okay, so my original function is square root of x plus 2. So we have f of x equals the square root of x plus 2. And we have f inverse of x is equal to x squared minus 2. Is that what it was? I think so. Yeah. Okay, so now what I want to do is I want to graph them on the same axis just to kind of show you. So we'll do this one first. So that's going to be, what is that going to look like, Alex? The x squared minus 2.
Isn't it going to be like half a parabola?
It's going to be a parabola that's going to move down 2, but we have to be really careful because notice here, it didn't say it, but what we really need to know is what our domain and range is, right? Because without that, we could have functions that aren't one-to-one. So is the square root of x plus 2 a one-to-one function? Do you know what this? Yes, it is it is. Do you know what the domain is?
Wouldn't it be 0 or no, -2 to infinity?
Excellent. Excellent. I'm just going to, because you knew it, I'm thrilled, but I want to show it for people who may be watching who don't know. So remember that always under the square root has to be greater than or equal to 0 for us to get a value. So all we have to do to find the domain is say x plus 2 is greater than or equal to 0, right? Because that's the only way I can take the square root, which means x is greater than or equal to -2, which is exactly what you said. So we start here at -2, and basically, let me put some lines in so I can get it a little bit cleaner. 5, 6, 7, 8, 9. Okay, so when I plug in, so it starts here at 0. That's 0. I can take the square root of 4. So let me make x equal to 2. That would be 2. And then let's make x equal to 7. 3, 4, 5, 6, 7. And that would be 9. So that would be 3, right? So if I were to do it, it's probably not a great job, but that's kind of what that square root looks like. And we know what the domain is, right? So now we know what the domain is. Do we know what the range is here? That's probably going to be very helpful for trying to graph our inverses. So what would the range for this function be?
It would be 0 to infinity.
Perfect. So this range is from 0 to infinity. Okay, good. So that means now I know what the domain of my inverse is, right? What's the domain of my inverse going to be?
0 to infinity.
Perfect. And the range is going to be?
-2 to infinity.
-2 to infinity. Perfect. Perfect. Okay, good. So my domain starts at 0. When x is 0, I start at -2. Let's see. When x is 2, that'll be 4 minus 2 is 2. So here, let me do it in a different color. So here, that could go there. And then, so my parabola is going to basically look like this. Okay. And if we can notice, let's see what I can do here. Color. make it, let's make it that, let's make it that color. So if I were to go draw my y equal x, notice how those are symmetric around that line.
Mhm.
And they meet right here because that point is 2, 2. And it has to meet there. Okay,
Mhm.
so that's basically that. And then let me see, I have one more slide. Okay, good. So here, this one's pretty simple, and then we'll be done. See, it wasn't too terrible today. So it says graph the inverse of this function. So how am I going to try to graph the inverse of this function?
Can't you just switch all the points?
Exactly. I'm just going to switch all the points. So I have this 0.01. I'm going to make it 1, 0. I have the 0.12. I'm going to make it 2, 1. I have the 0.24. I'm going to make it 4, 2. Let's see, 2, 3, 4, 1, 2. Okay. And I notice as I get closer and closer to the x-axis, as I get more and more negative, I get closer and closer to the x-axis. So I'm assuming there's a horizontal asymptote there, which means that I'm going to have a vertical asymptote on my inverse function.
Mhm.
So it's going to look something like that. And we can see again, let me see if I can do it better in this color. We can see that we have the line symmetric along the y equal x. This is y equal x. And it does look pretty symmetric. It's nice because I have grid lines, so it made it a lot easier to see it. And that's basically it. That's basically one-to-one and inverse functions.
Okay.
Any questions about any of it?
No.
All righty then. Let me stop sharing. Let me stop recording.